Good morning. So, welcome to the last lecture in this course now. We've had a long semester, but let's look at this one last topic today, which is on mass transfer. But before I go there, let me say a few things about heat exchangers that I could not complete in the last class. So, what I wanted to say here is that you look at all the three heat exchangers, or at least the effectiveness NTU relationships that I have shown here for parallel flow, counter flow, and shell and multiple of two tube passes or tube pass heat exchanger or shell and tube heat exchanger. So in these cases, there are some in all of these cases there are some similarities, some features that you should always note. Of course, one thing that you should notice is that the effectiveness is always between 0 and 1. So it is a fraction number which will be always bounded. The second part is that if you look at, let me just zoom in one particular picture here. If I look at this picture, and let's just use a different color just for this explanation. So if you look at this figure and you see that the way effectiveness increases versus NTU, right, you can see that the effectiveness actually increases quite rapidly till about maybe NTU of about 1.5. Okay, this is the point till which it is actually increasing. Beyond NTU of 1.5, the effectiveness actually is growing slowly. Now, as you remember, I mentioned that NTU is a measure of the size of the heat exchanger. So definitely we want an exchanger with a high effectiveness. But we also know that to get to a high effectiveness, the NTU has to be very large. And further, beyond NTU of 1.5, the effectiveness does not increase, or it increases slowly. So so even though a high NTU might be good from a technical or a heat transfer point of view, a high NTU will also mean a more expensive heat exchanger because the size will come into play. So it may not be economical per se. The other thing is that if you compare the three heat exchangers that have the three effectiveness relationships that I've shown here, it is also easy to see that for the same NTU, or at least I hope that you can make out from the pictures that I also put up in the last lecture notes. For the same NTU, the counterflow heat exchanger gives the highest effectiveness. Okay, so that is quite understood that counterflow works best. After counterflow is actually, which I have not shown here, is the cross flow heat exchanger in which the two fluids are unmixed. So that picture I think is available, or that sketch is available in the book. You can go and check. Also, between 0 and NTU of 0 and zero point 0.3, maybe let me take this example here now. Between NTU of 0 to maybe 0.3 would be somewhere here. So between this range of NTU, the effectiveness is actually almost the same, or it's independent of the heat capacity ratio or the rate of heat capacity ratio. So till about this point, which maybe I can denote here, till about maybe NTU of 0.3, right, the effectiveness is independent of CR. So, and that's true for all heat exchangers, not just for this heat exchanger, but it's true for all heat exchangers that you can check. Okay, so that is something that you should also remember. For all these cases, also one common feature is that the effectiveness is lowest for the rate of for CR value of 1. So in all cases, lowest effectiveness happens to be when the two fluids have the same heat capacity or rate of or ratio of the heat capacity rates is 1. Finally, let me just close this by saying that if CR is 0, then all heat exchangers give the same effectiveness. In this case, effectiveness would be 1 minus exponential of minus NTU. And that basically means that these curves that I've shown here, the curve which is on the top, which is for CR0, this is actually the same curve in all heat exchangers. It does not change. Okay, and that is given by this functional form. So that the effectiveness is 1 minus exponential minus NTU. Now, please remember that what CR equal to 0 means. CR0 will mean that one of the fluids is actually having a phase change. So In case it is a condensation process or a boiling process on either end, this will actually correspond to CR0. And so for that, we don't have to rely on these charts. We can actually simply pick up this equation and calculate the effectiveness. Okay, so this is all that I had to say about heat exchanges. Let me now begin discussion on the last topic in this course, which is diffusion mass transfer. Now, we did deal with mass transfer. We did deal with mass transfer when you're looking at convection, right? So we derived some mass transfer correlations as well. What we were dealing with there was mass moving because of bulk motion. Here, what we are dealing with is diffusion type of mass transfer, which is mass transfer due to concentration gradient or concentration difference in a mixture. So it is similar to heat conduction. In heat conduction, recall that the presence of a temperature gradient gave us a heat flux. In this case, what we are saying is that the presence of a concentration gradient will lead to some kind of mass flux or molar flux. Okay, so that in that sense, it is sort of analogous. Okay, so in this case, in either cases, these were the driving potentials. So the gradients were the driving potentials for the movement of the, if I can say, matter could be energy, or in this case, mass. Now, what we are dealing with in this case, what is different from the earlier part, in which I will make it more clear in the later part of this lecture today, is that we're talking about diffusion. So we're talking of mass transfer that describes the relative motion. Okay, remember this one. It describes the relative motion of species in a mixture, and that is only because of concentration gradients. So relative motion, we are interested in relative motion of a species in a mixture, and that relative motion is due to concentration gradients. And in fact, that is how it is different from what we have done earlier. And this relative motion that I'm talking about, because of concentration gradient, it's very as I say, it's very similar to heat conduction. Remember, heat conduction was also because of molecular activity. Okay, so concentration, or other diffusion mass transfer, is also similar in that sense that it is also derived because of molecular activity or random motion of molecules of a substance. The simplest example that I can give is that if you, let's say, uh, you have a room and you spray let's say, a perfume on one end of the room. So even if there is no motion in the room, even if the fans are off and there is no driving motion for the bulk flow, you may be standing on the other end of the room, but at some point you will be able to smell, or your nostrils will actually be able to detect that there is a good or a bad smell. I don't know, but there is a smell, that has been created. So that happens purely because of random walk or random motion. Okay, now diffusion, as I'm talking about here, it happens most readily in gases and least in solids, for the simple reason that it also depends on intermolecular spacing. So if you're in a gas, as I said, the perfume example is for a gas where you have, you create very fine liquid droplets. And so in a system, you have these molecules which are far away. The liquid also evaporates as it moves through. So because the molecules are far apart, so it takes much sooner, or the rate of transport is much faster in the gas as compared to maybe in a liquid or a solid, where the intermolecular spacing is lower. So we talked about the diffusion mass transfer. We said this is the driving force or driving potential, which is the gradient of concentration. So let's first describe what is concentration, or how do we define concentration of a species. So let's say a mixture has n constituents, And I can define the concentration in two ways for these constituents. I could either use a mass density, which I'm going to denote as rho I. So this is mass density of species I, which would be in kilograms per meter cube. Or I can define the molar density, or which is more appropriately called molar concentration of species I. And for the purpose of this course, to be consistent with the SI units, we use this as kilomole per meter cube, not mole per meter cube. Please remember that. So we can define molar concentration as Ci. The two are not independent of each other. In fact, rho I can be written as concentration of I into molecular weight of I. Okay, this is the molecular weight of species I, which is again in kilogram per kilomole. Normally we report molecular weight in gram per mole, so we have sort of, it's the same value. For example, carbon will be 12 kilogram per kilomole, which is 12 gram per mole, but because kilo is there in our SI units in most cases, so we're just following with that kilogram notation. Using the mass density of each species or the molar concentration, we can also define the mixture density, which would be, let's say, rho, which is summation of rho I, so sum over all constituents. And we can also define the mixture concentration, which would be C. I'm going to use a symbol capital C for that, which would be summation Ci. And using the mixture density and mixture concentration, I can define two more quantities which are more commonly used in all diffusion mass transfer analysis. These are the mass fraction and the mole fraction. So I can define mass fraction Mi of a species I as density rho I by capital, you can say summation rho I or just rho. And we can define mole fraction. We will use a symbol x for that. So xi, not to be confused with the coordinates. Okay, so just remember this. Xi will be Ci by C. And in both cases, you can check that quite clearly. Summation Mi would be 1, and so would summation xi. Further, if we were dealing with a mixture of ideal gases, right? So let's say, let me take the example of air. If I could say that air is a mixture of ideal gases, I could use Dalton's law of partial pressures and write that the mole fraction xi for that mixture, which is, as I said, a ratio of Ci by C, is the same as the partial pressure of the gas, specific gas, versus the total pressure of the gas. And this comes because, as I said, if we are assuming ideal gases to be making this mixture, okay, and in ideal gases, I know that concentration, for instance, will be proportional to the pressure. So concentration will just be Pi by universal gas constant by temperature. So it's the same thing then. Mole fraction is also the same as ratio of partial pressure to the total pressure. And this you have used. I know this you would have used in many courses, including the last one that you may have done, energy systems. When we were doing it, looking at psychrometry, I'm sure you have used this relationship. Okay, so this is just to set up some groundwork for what now we get to diffusion mass transfer. So diffusion mass transfer is given in terms of another phenomenological model, which is called as Fick's law of diffusion. Similar to Fourier's law of heat conduction, Fick's law of diffusion states something about the flux. Okay, in Fourier's law we said flux is proportional to temperature gradient. Here again we will say flux is proportional to a concentration gradient, and we will do this. Most cases that we will deal with in this part of this course would be on binary mixture. So I think I defined binary mixture in convection, but let me say this again. We have a binary mixture now, which is a mixture composed of two species. Okay, let's say A and B. There are two species A and B in this binary mixture. That's why we call it binary. So what Fick's law states is, let's say the mass flux. Let me take this first. Mass flux, which I'm going to denote as symbol small j of A, let's say, and it's a vector, similar to Fourier's law where we wrote where we wrote the flux as a vector. So mass flux is proportional to the gradient of the concentration, but more specifically, gradient of the mass fraction. So Fick's law says that Ja is given as minus rho into dAb into gradient of Ma, where rho is the mixture density and dAb is what we call as the binary diffusion coefficient. And this number actually came way back, especially when we were looking at Schmidt number. Okay, its units are meter square per second. So it's binary diffusion coefficient, sometimes also called as mass diffusivity, or even, yeah, mass diffusivity is more commonly used. I would not say diffusivity because then diffusivity gets confused with something else. But yeah, it's mass diffusivity. Similar to mass flux, we can also write molar flux. The Fick's law will also be applicable here. So in molar flux, we will use a symbol capital J with a star. That's what your book also uses. So mass or molar flux is minus C times dAb into gradient of XA. So Fick's law is saying that the molar flux will be proportional to the gradient of the molar fraction or the mole fraction. For a binary mixture, you can even think of it this way, that C into C is a total concentration, which is sum of two constituents. So you can, if C is constant, let's say total concentration is constant, this becomes Ja star equal to minus dAb into gradient of Ca. Okay, so that becomes even more apparent or more in tune with the heat conduction. Okay, C into Xa is actually Ca. Okay, so there are some similarities of mass diffusion or diffusion mass transfer with heat conduction, but there are also differences, and the differences are quite complicated. And so let me take some time to explain what are the possible differences. And to explain this, let me take an example. So let's take a hypothetical scenario. Let's say we have a some kind of a system in which I have a soft partition, which means I can somehow remove it. Maybe it's like a sliding door. I have put a sliding door in the channel. Hmm? The channel is insulated in all sense that it is it is not losing any mass from other side. It's just separating, maybe long channel, but has a door which separates mixture of A and B, in which the, let's say the concentration of A is Ca1 here and it's Ca2 here, and Ca1 and Ca2 are not the same. Okay, so we can also plot something like this. So let's just start the plot as well to explain what is going to happen. So say we have let me take, I think the simplest would be to take Ca1. Yeah, that would make more sense. So Ca1 is, let's say, less than Ca2. So I'm going to plot concentration on the y-axis and the position on the x-axis. So say initially we had a distribution of this type. This was the concentration of A, and this is a soft partition which is separating these two mixtures. Now say I remove this partition at t equal to 0. If I remove this partition, what do we expect? And let's say the partition, in fact, the fluid itself, the whole mixture, let's say, uh, if I look at the interface, which is this region, if I call this as the interface, let's say this was not moving. Okay, this was stationary. If it was not moving, then as soon as I remove the partition, I can see that the concentrations are not going to be the same, and there is more. Remember this, I said this is a random walk or random movement process. So what will happen is, right at the interface here, molecules from A, from this side, from the right side, will actually cross over here, because there is more of A here and less number of A, so they will actually, there would be net transfer to the right. So A will actually diffuse, as I now I'm saying the word, it will diffuse to the left side. So you will have maybe a distribution which would maybe right after time t0, which would look like, and I'm drawing it intentionally slightly lower. It doesn't mean the concentration is lower. I just don't want it to overlap. So maybe the concentration would be somewhat like this, just after t0. And as time goes on, these concentrations will actually flatten out. So this is with time. As time goes on, you will see that the concentration is flattening. Right? It is balancing. So the gradients are going to be established. And of course, the whole thing, I'm assuming here that the two ends, the two mixtures are infinitely, or the channels are infinitely long, because of which I'm not showing any substantial increase here, but of course they will increase. So eventually, at some point, the whole thing, if I can maybe put it this way, at some point the whole thing will reach the same concentration, maybe at time infinity. But I'm not very concerned with that. Okay, this is not. If I say that the channel, that mixtures are occupy infinite amount of space, then this will never happen. But just for you to know, physically this is going to happen. So anyway, so we know that this is going to happen if the interface was not moving. But let's say if the fluid itself, the mixtures were part of a fluid system and they are moving, so the interface itself is also moving. So then you won't see this kind of a behavior. In fact, because this interface itself that I've drawn here would actually have moved after some time. It would have moved to the right. Let's say the flow was from left to right. This interface would go to the right. And so what happens is that the way the Fick's law was written, and now coming back to this, the Fick's law was written actually for a system which is stationary. Or in other words, it is written for a system in which the interface, or rather you are looking at the process which is fixed to the frame of reference of the interface. Okay, so you're moving with the same velocity as the interface. In that sense, if you're moving with the same velocity, then you see what is going back and forth, then you see the diffusion, but if you are standing as a stationary observer somewhere, maybe you are standing somewhere here and observing what is going on at a fixed point, and the interface was moving, then you would not see diffusion, you would actually see bulk motion. You would not be able to categorize what is bulk and what is diffusion. So Fick's law that I've written here, now let me say this very clearly. Okay, so this is written when you are dealing with transport that of A, which is relative to the mixture mass, or let me say molar average velocity. If you were moving with the mixture average velocity, then you would see this diffusion, or you can observe this clearly. But if you're standing as an observer somewhere, then this is not the flux. because it is the whole system is also, the whole mixture is also moving with some velocity. So how do we tackle this? Of course, Fick's law is valid. It should not mean that Fick's law is not valid, or it is not of any use, but it is actually has a very strong uh, use. But how do we identify, or how do we separate Fick's law or the diffusion mass transfer from the bulk transfer of any species? And now what? So now let me also reiterate whatever we were doing till the convection part, which was convection mass transfer. There we were dealing with bulk transfer. We didn't talk about diffusion anywhere. So to show you how this is tackled, let's again consider a binary mixture of A and B. So there are two species only in a mixture in this case. Now what we will try and do is to calculate the absolute flux of A. And of course, we don't need to do B, but we can do absolute flux of A to start with. And this will be relative to a fixed coordinate system. So now we are not moving with the fluid or with the interface. Interface is sort of like a simple way of explaining what you may expect, but the whole fluid may actually be in motion and there may not be an interface. So the absolute flux, which I'm going to represent by n double dash and let's say subscript A, this is the absolute flux of A. This should be written as, or this can be given as, the concentration of A into the velocity of A at a given location. So VA is the average velocity of all A particles at a given location, or all particles of A at that location. Similarly, I can write the absolute flux of B to be CB into VB, which is again concentration of B at a given location into velocity of B, or all particles of B at that location, average velocity of all B particles. So using this, we can define what would be a molar average velocity for the mixture. So if you look at molar average velocity, which I'm going to now represent as V star, this I can calculate by saying that C into the total concentration into V star should be sum of the individual contributions. So that is what is molar average. And so clearly V star would be XA VA plus XB VB, where C is CA plus CB. That is the total concentration of the mixture. Now, though this may look very simple, but this is actually quite an important equation here, as we will see that this knowing V star, and if I know the local concentration, I can recover the total flux of the mixture, or not of the species, but of the mixture. So we will actually use this at some point, just to make a few more observations about Fick's law. Okay. Now, what we want in our for us to characterize diffusion is to somehow, so as you remember, as I mentioned, if we move with the velocity of the mixture, then we can observe diffusion, right? We are moving with the same frame of reference the of the process of the bulk flow process. So there you can see which way molecules are going because of random activity, because of random motion. So we can define now molar flux of A relative to the molar or the mixture molar average velocity. So if I write this as let's say CA. Remember, A is moving with velocity VA and the mixture is moving with V star. So if I want to observe what is happening with those A particles at that location, I need to move with the mixture average velocity, which is at that point. So V star, this should then be the flux because of diffusion. So that is what relative is. As I mentioned in the early part, when I was starting this lecture, that you will get more concerned about relative transport. So this is what relative transport is. Now, what does this come out to be? Now, CAVA is actually N double dash A, and the second term would just be CAV star. And so the total flux is CAV star plus J star A. So we have the total flux has two contributions. The total flux has two contributions. One is because of bulk motion or flux due to bulk motion with the mixture average velocity. And the second part is the diffusive flux, which you can also say is the relative motion of particles of A. And note that N double dash A that I've written here, it is the absolute flux of A or total flux of A. But that is measured with respect to a fixed coordinate system, not a moving coordinate system. So we can write this equation in a slightly more different form as well. I can still say that N double dash A is minus CDAB gradient of XA plus CA. It is CAV star, so I'm going to write this as CA by C into CV star. For the reason that I want to replace CA by the mole fraction of A. Okay, so this becomes minus CDAB gradient XA plus XA. Now CV star, this number here, is actually the total flux. Remember, in fact, when I wrote it here, I should have mentioned this. I did mention actually. I said if you multiply V star with C, the total concentration, you would get the total flux, because that is sum of N double dash A plus N double dash B. Right? N double dash A was CAVA and N double dash B is CBVB. So that is the total flux. So CV star is a total flux, which is N double dash, but I can just say this is N double dash A plus N double dash B. And this is N double dash A. So this becomes the flux equation in mass transfer. Similarly, we can write N double dash B. So N double dash B would be minus CDBA, let's say, into gradient of XB plus XB N double dash A plus N double dash B. So basically replace A by B, and that the subscript A by B, and you get the equation for B in a binary mixture. But here is the catch now. If you now compare this flux equation with Fourier's law. Now remember Fourier's law, if there is no motion and you're only dealing with conduction, then Fourier's law is actually written with respect to a fixed or you're writing Fourier's law when you're observing diffusion from a fixed coordinate system. Here, even if you observe it from a fixed coordinate system, though you get flux has this diffusive part, but you get this additional contribution, which may or may not be zero. So this is where things get complicated, and this is where there is a departure from heat conduction. So this additional term that you're getting makes mass transfer different from heat conduction. So it is not analogous anymore, unless this number xa into n double dash a plus n double dash b was 0. This is not possible. Okay, but there is one special idea. In fact, I should have mentioned this earlier. I wrote that the flux sort of, I said J star A, I wrote as minus C D A B gradient XA. Similarly, J star B would be minus C D B A. Now, A, basically C D A B is sort of diffusion of A in B, and B A is B diffusion of B in A. Okay, binary diffusion coefficient. But I didn't say anything about whether the diffusion coefficients are equal or not. It so happens that DAB is DBA, and mathematically you can prove it quite easily by looking at the definition of JA star, the alternate definition, which was CA VA minus V star, and JB star would have been CB VB minus V star. If you add the two equations, right, if I add them, I would actually get, I would get, left hand side would have J star plus JB star, and the right side would be 0. And so that means that if you substitute, that in a binary mixture XA or XB, rather, let's say XB is 1 minus XA, if you plug in, you can actually prove that DAB will be DBA from here. So something that I intentionally didn't want to cover, but I'm just leaving it, just telling you that this is how you get to this point. Now, this is just some, I went a little sidetracked. I got sidetracked, so I started putting all these things together. But I'm more concerned or more interested in a scenario where V star is 0. So if the mixture molar average velocity was 0, what happens there? Which is what is the case where I was saying that the interface is on moving. So if the mixture mole average density or mole average velocity is 0, clearly n double dash A, which we wrote as CA V star plus J star. So we wrote as CA V star plus JA star. So this is 0, and this becomes just JA star. And so basically the total flux then is only because of a diffusive part. In these scenarios, when the total flux is only the diffusive flux and the mixture average velocity is 0, in those scenarios we get complete analogy between diffusive mass transfer and heat conduction, or diffusive heat transfer, if you want to say it. These scenarios where VA star or V star is 0 are called as, or these mediums where this happens, these are called as stationary mediums or stationary systems. Okay, and the approximation is also called as stationary medium approximation. And we'll see how this approximation can be applied in some of our problems. Okay, so the flux has been established now. Now we need to look at conservation. So far we only wrote about rate of things, but we also need to conserve matter. So when we look at conservation of species, we invoke the same conservation principles that we have always been using. So for a certain control volume, we have a control surface. Okay, so this is the control surface for the control volume. And we look at rates at which, let's say, species A in this case enters, the rate at which it leaves, the rate at which maybe it is generated because of a chemical reaction, and then the rate at which it gets stored in this control volume. And so, similar to all conservation principles, we will say m dot a in minus m dot a out plus m dot a, let's say generation G, is dma dt, which is sort of m dot a storage. So the same equation is applied, and it's the same derivation. Take an infinitesimal control volume, write the fluxes on all the faces of the control volume, include all terms in this manner. For an infinitesimal volume, you also take an infinitesimal element size, so the volume size, which is delta x, delta y, delta z, so and so forth. I'm not going to go into the derivation there, except that you can finally obtain a simplified form of conservation equation, a partial differential equation for conserving this species A, uh, for under certain approximations or under certain assumptions. So we will be assuming the following. We will be assuming a mixture that is homogeneous of A and B. So it's a binary mixture. And secondly, the mixture is stationary. So there is no, so the medium is stationary. So there is no bulk flow in the mixture. If there is bulk flow, then the problem becomes slightly difficult, but it comes down to a similar form, or the equation that we can derive has a similar form, the same way as we did for convection. So you get convective terms in the equation and in the differential equation. But here we can actually have a very simplified diffusion equation, which is also called as a mass diffusion equation, which would be d by dx into c dab dxa dx plus d by dy c dab dxa dy plus d by dz c dab dxa dz plus any generation term, which is, let's say, n dot a. This is equal to dca dt, rate of change of concentration of species A. So it is almost the same as the heat diffusion equation that we had derived in, I think, lecture 4, I think, if I remember, lecture 3 or lecture 4. But it's the same equation, except now the variable has changed. Instead of temperature, now we have the mole fraction as the variable, and instead of conductivity, thermal conductivity, which came in there, we have the mass diffusivity. Okay, so that is the reason I'm going through the same mathematical treatment. But there are some special cases for this equation, and I will consider some of them here today. First of all, if C was constant, the total concentration was constant in this binary mixture, and also DAB was constant, then we get a much cleaner form of this differential equation. Then we can write this as d2 Ca dx square plus d2 Ca dy square plus d2 Ca dz square plus n dot a by dab would be 1 by dab dca dt, where I've used the idea that, so C is constant, so I could take C inside the gradient. So basically what I've used is C into dxa, let's say dx, just one thing, would be d by dx of cxa, which is Ca. If C was not constant, I could not have written it this way. Now, similar equations can also be derived for cylindrical and spherical coordinates. So this is just, as engineers, we don't need to do all this derivation here, but you can actually check if there are these equations that are available. So again, I'm not, in the interest of time, I'm not going to derive them. Now, what is of more interest to this class is, for this last lecture, is to see some classification based on this n dot a term. So there are some classifications based on the form of n dot a. And I will not be able to take up all classifications, but I will take some examples very soon now to describe how n dot a, because n dot a, remember, is a generation term. So generation could be of different types. So I will take maybe at least one example of how a generation term can influence the outcome in mass transfer. There are some few more examples in the book, which I suggest you to go and look at. So that is one aspect. The other one is, now let me say that we did this for a stationary medium, or we assume that the medium is stationary, but all mediums may not be stationary. And if we want to calculate or understand how concentration can be obtained in those cases, so what can we do? Okay, so if I look at the flux equation again, so if I look at, let's say, non-stationary medium, in which the flux equation was minus c dab gradient of xa plus xa times n double dash a plus n double dash b. Okay, so say that I am working in a system where, if the flux of species b is negligible, say if we have a scenario where flux of species b is negligible, which would mean that this will drop off. Okay, this is a small number. And if the mole fraction of a is much less than 1, which would mean these kind of systems are called as dilute mixtures, where the mole fraction is very small, or the mass fraction is very small. So if that was the case, then I can pull this term here. I will have a 1 minus xa times n double dash a. Xa being much smaller than 1, it would just lead to n double dash a only. So the flux equation in that case would be approximately the same, but it would only have the diffuser part. So in such cases where these two conditions can be somehow obtained, where the flux of, let's say, species b, in this case a dominant species, because a is present in very small amounts, if the flux of the dominant species is nearly zero, and the mole fraction, of course, is much, the minus species is much smaller than 1, it's not just small, it is much smaller than 1, in that case the flux becomes the same as the flux given by Fick's law, and so the stationary medium approximation can be invoked. Right, can be applied. So typically in mass transfer problems, we try and simplify to get a governing equation by using this approximation. If this was not valid, by the way, let me also be very clear here, if this was still not valid, then the governing equation that we would have would not be this differential equation that I've written here. Okay, it would not be these two differential equations, in fact not the first one, which is a more general case. Instead of this term that we have here, we will actually have a minus d by dx of n double dash a. Okay, plus, let's say, so basically you will have a flux term there, not the actual gradient term, but you will have the total flux term. It is just that it's a matter of fact that, or very similar to, if you remember, in heat conduction we also had the same thing. The flux is later put in, or the rate of transport of the species is later put in into the governing equation. Otherwise, we actually have minus dqx dx plus, or rather minus dqy dy, and then minus dqz dz. So that is how the conservation rule comes in. This adding this is basically a consequence that the main fluxes, okay, or rather the mole fractions are small, or the medium is stationary to start with. That the velocity of the mixture is zero. But now what I'm saying is that if the mixture velocity is still not zero, it can still be applied as long as these conditions can be somehow satisfied. Okay. Now, when does this happen? It may sound like very unreasonable, but this actually can happen in some scenarios. So these conditions can be met in two specific cases. One is, of course, I have said that it's a dilute system, so it could be a dilute gas or liquid mixture. So something which has gases in a mixture, which is gases in a small amount or liquid in a small amount, and the motion of the solvent is negligible. So under that case, this can still be applied. Or the second case, where this is more predominantly applied, is when you have species diffusion in a solid. So when you have a solid membrane and something is diffusing through the solid membrane, then this is quite easy to apply, because the solid is anyway not moving, even though it is there. Okay. All right. So now for this, let's say we have a stationary medium. Somehow one of the conditions is satisfying. One of them, these cases is applicable for us, and we want to solve this differential equation. So we need one initial condition. As you can see, we need one initial condition because we have a time derivative here, and you need two boundary conditions in each direction because you have second order derivatives. So initial condition is typically specified in terms of the concentration itself, but the boundary conditions can be of different types. So the simplest type of boundary condition is the Dirichlet type, where you are given, let's say, the mass fraction or the mole fraction of species A at some location x naught at all times. Let's say that is specified. So that becomes one condition to solve this problem. The second type of boundary condition could be the Neumann type or the flux boundary condition. So let's say a constant species flux is given, which is, let's say, J star A at some point, which is, let's say, this at the surface. So this could then be written as minus C DAB dxa dx, let's say at that location x, where x is the perpendicular there in terms of at that location. So most problems that we deal even in diffusion mass transfer have the same analogy as conduction heat transfer, that the same type of boundary conditions come in, and as expected, same kind of solutions will emerge. So the simplest case could be, let's say we have a 1D system. Say we are given some concentration of species. Let's say XA S1 is here, XA S2 is here. This is a mixture of, let's say, A and B, a binary mixture. The thickness of the slab, solid slab, is, let's say, L, and we are concerned, we want to know the concentration distribution and the flux through this medium. So as expected, we can quite easily guess that the concentration gradient will, or the concentration distribution would be linear if there is no generation. Let's say n dot A is 0. I should be very clear about that, right? And then in that case, the equation would have been d by dx C dab dxa dx is 0, which is what is giving us a linear linear concentration distribution. And so xa would be xa, let's say s2 minus xa s1 by L into x plus xa s1. And the flux would basically be, so let's say flux, sorry, not vector now. So n double dash a along x, say, would just be c times dab xas1 minus xas2 by L, which I can also write as dab by L cas1 minus cas2. So exactly the same way of calculating the distribution and the flux as we used in diffusion, as we used in heat conduction. So there is no change. Okay. Now let me take one more example, which is sort of a follow up from what I said about classification of this equation based on the form of n dot a. So the second example that I can take is when you have a chemical reaction occurring in the mixture. So say now that we have again a binary mixture of A and B, and we have a homogeneous chemical reaction, which means that it is occurring in all parts of the mixture, even though it may be variable in its intensity, which means that it is not uniform, but it can be non-uniform, but it is happening everywhere in the mixture. Okay, so it's a volumetric phenomena. So now, assuming again 1D type of behavior, okay, a 1D system, we can write dab d2ca dx square plus, let's say, n dot a is 0. That would be the governing equation for this system. And perfect, it has perfect analogy with the if n dot a was constant, by the way, it would have perfect analogy with what we did for heat generation in a constant heat generation in the case of heat conduction problems, 1D heat conduction problems. Except now here, because it's a chemical reaction, so chemical reactions do not necessarily happen at constant rate, so they depend on rates of reaction. And depending on different rates of reaction, we can have different solutions. For instance, if we had a zeroth order reaction, in which case what you typically would see is that n dot a would just be some constant. It would not depend on the species which is reacting. So the solution there is quite easily obtained. But if you have a first order reaction, which is more commonly the case in much of mass transfer, in this case, for instance, I can write n dot a to be minus k1 times c of a. That is typical of a first order reaction, where k1 is the rate constant, and of course negative sign indicates that a is consumed. If a was being produced, then this will be a plus sign there. But just for the purpose of this thing, let's say that that a is getting consumed in this system. So what do we get? We get, for this reaction, we get dab d2ca dx square minus k1 ca is 0. That is the governing equation, and that is actually the same equation as you saw in fins or extended surfaces. So ca would be some c1 e to the power, let's say, mx plus c2 e to the power minus mx, where m square becomes k1 by dab. So that doesn't change, right? It is the same hyperbolic type of solution that you expect. Now let's look at one specific example where this can be applied. Say the system is something like this. We have a system in which, let's say, we have a liquid B exposed to, let's say, A in the gas phase. Let's say the bottom surface is impermeable. All surfaces are impermeable, but the bottom surface is definitely impermeable. say we define our coordinate system from here, from the interface, and let's say that we know the concentration of A here, Ca naught, from some thermodynamic relationship. Okay, if the height of this liquid is, let's say, L, then I need to apply two boundary conditions to obtain this solution, right? To obtain C1 and C2. Okay, so the question, the problem that we're dealing with is there's a gas that dissolves in liquid B, and as it dissolves and it moves, as it diffuses through B, it also reacts. It also maybe gets consumed in a chemical reaction. So what should be the profile, the concentration profile in B, and what should be the flux of A at that interface? The concentration there is known, but the flux is not known. So that flux will dictate the rate at which A is getting consumed, sort of, in the liquid. So the boundary conditions would be, for instance, in this case, Ca at x equal to 0 is just Ca naught. And so we get C1 plus C2 is Ca naught. The second boundary condition comes from this impermeable surface. An impermeable surface is here is one in which the substance cannot propagate any further. So that would mean the diffusion or the flux, so dCA dx at x equal to L should be 0. So the flux of A, which is in this case characterized by the concentration gradient, that should be 0. So we can take the derivatives, put x equal to L, calculate or derive another equation for C1 and C2, then solve the two equations and get a final solution. So the final solution would be somewhat like Ca would be Ca naught times e to the power mx e to the power minus ml plus e to the power minus mx e to the power ml by eml plus e minus ml. And using this, we can then derive the flux of A at the gas liquid interface, which, as I said, will dictate the rate at which A is getting dissolved in B. So this flux J A star at x equal to 0 would just be, or rather I should say total flux now. Why am I just writing J? So N double dash A at x equal to 0, or in fact the vector is also gone now because this is only along x. So let me say Na x at x0 would be minus C times D AB dxa dx at x equal to 0. And of course, since one of the assumptions that I'm not showing here is that the total mixture concentration was same, so this could be minus, also written as minus dab dca dx at x0, and this comes out to be Ca naught times dab m times tan hyperbolic ml. And this, if you recall, this was also similar to what we obtained in the case of fins. Then we were looking at fins in our in the extended surface analysis. We got a flux equation which also looked like this. Okay, so anyway, I'm going to stop here. Thank you.